Today we'll study something which is very important for Olympiad problems and which is p-adic valuation of factorials. So if p is any prime number, then p-adic valuation of factorial n is nothing but it is the highest power of prime number p which divides factorial n. And the notation for that is we are going to write it as v and this subscript p and factorial n. And all of us know this legendary formula, which is Vp factorial n is the summation I varies from 1 to infinite greatest integer function of n upon p to the power I, or floor function of n upon p to the power I. So which is n upon p plus greater function of n upon p square greatest integer function of n upon p cube, and it goes up to infinite. So after a while, when this power of p is greater than n, so for all successive cases its value will be 0, then we'll get a finite result. So we are not interested in this formula because it is very common and it is self-explanatory. So we want to prove another theorem, which is Vp factorial n is equal to n minus Spn upon p minus 1, where Sp denotes sum of digits of n in the base p. So what I'll do is I'll write this n in this base p. So I'll write it as a0 p to the power 0, a1 p to the power 1, a2 p to the power 2, and then ak and p to the power k, where this leading digit is ak. So this ak, it should be 1, or it should lie between 1 and p minus 1, and any other ai should lie between 0 and p minus 1 for all i's between 0 to k minus 1. So this is how we can express this number n to the base p. So I can also write it as summation ai p to the power I, where I varies from 0 to k. Now we'll use Legendre's formula. So I'll write Vpn as this summation. I'll take this as j. J varies from 1 to infinite and n upon p to the power j. So I can also write it as summation j varies from 1 to infinite, and this is, what is n? N is this summation ai p to the power I, where I varies from 0 to k upon p to the power j. So I'll write it as summation j varies from 1 to infinite, and this is this double summation I varies from 0 to k ai and p to the power I minus j. So whenever I is j or greater than j, in that case I'll get an integral value from this. So all I need to do is I can simply write it as summation j varies from, and when I is equal to j, so there in that case it will be aj, then aj plus 1 into p, aj plus 2 into p square, and then finally it will be ak and p to the power k minus j. Now if I'll put this summation, so if I'll put j as 1, I'll get a1, a2p, a3p square, and then ak p to the power of k minus 1. If I put j as 2, it will start with a2, so I'll write a2, a3p, a4p square, and then ak p to the power k minus 1, and it will continue till the value of j is equal to k. So if the value of j is equal to k, so then in that case I'll get this as a to the power k into p to the power 0. So I can rearrange it as a1, there is only one a1, and then I can write a2 into 1 plus p, a3 into 1 plus p square, and then finally it will be ak, it will be 1 plus p square, and it goes up to p to the power of k minus 1. So I can express it as another summation, and which is Vpn as this summation, suppose it is ai, and if it is a1 then it is 1, a2 it is 1 plus p, if it is ai then it is 1 plus p square, and it goes all the way up to p to the power of I minus 1. Now 1 plus p square up to p to the power I minus 1 is nothing but a geometric progression. So I'll sum this geometric progression. So I'll write the summation as ai, and this is p to the power I minus 1 upon p minus 1. So this is summation ai p to the power I minus 1 upon p minus 1, and that's the value of Vpn. Now we'll take the right hand side. So we'll take right hand side. We can write right hand side as n minus Spn upon p minus 1. Now n is this summation, which is ai p to the power I, where this I varies from 0 to k, and minus what is Spn? Spn is sum of digits of n on the base p. So this is nothing but this is summation I varies from 0 to k, and that is ai upon p minus 1. So I can write it as summation I varies from 0 to k. Now here I can take ai common, so I write ai p to the power I minus 1 upon p minus 1. Now we look at right hand side, and if we look at the result on the left hand side, then it is also ai p to the power I minus 1 upon p minus 1. Here also the value of I varies from 0 to k. So in this case, left hand side is equal to right hand side. So from here we'll say this Vp of factorial n, or p-adic value of factorial n for this prime number p, is n minus Spn upon p minus 1, where Sp denotes sum of digits of n in the base p. Now let us take an example. So this is a problem which appeared in Canadian Mathematics Olympiad, and the question was, find all positive integers n such that 2 to the power n minus 1 divides factorial n. So what I'll do is, here I'll take this p as 2, and I'll express this n to the base 2. So I'll write this n as a0 2 to the power 0, a1 into 2, a2 into 2 square, and then ak into 2 to the power of k, where ak is equal to 1, and then each of ai is either 0 or 1 for all I that lies between 0 and k minus 1. Now if we'll use this theorem, then p-adic valuation of 2 in factorial n will be n minus Spn upon p minus 1. P in this case is 2 minus 1. So the number should be divisible by 2 to the power n minus 1. So that means this number should be greater than or equal to n minus 1. So we'll simplify. We'll write n minus Spn should be greater than or equal to n minus 1, which is Spn should be less than or equal to 1, which simply means sum of all coefficients a1 plus a2, a0 plus a1 plus a2 plus ak should be less than or equal to 1. Now since ak is 1, this summation cannot be less than 1. So in this case, I'll get a0 plus a1 plus a2 and plus ak minus 1 should be equal to 0. Now these coefficients, they cannot be negative. So that means for each of these numbers, a0, a1, a2, all these coefficients, ak minus 1, they'll be simply 0. So this number n, it should be of the form ak is 1 into 2 to the power k. So whenever n is of the form 2 to the power k, then for all positive integers, 2 to the power n minus 1 will divide factorial n. And that is the answer to this question.